Hello again, this is the Pencrest High School AP Physics 1 video series. This is video 8A, Introduction to Waves. Very simply, a wave carries energy away from a disturbance of some kind. If you think about throwing a rock into a pond or a puddle, imagine that the surface of the pond is calm. When the rock hits the water, that provides the disturbance, and then the waves move through the water away from the disturbance, carrying energy away from that spot as they go. The matter that carries the waves is called a medium. In this case, the water would be the medium. Wave medium can be solid, liquid, or gas. We'll hit that to a greater extent later on. There are a number of different types of waves. We're going to look at two different types of mechanical waves. First, we're going to look at transverse waves. In this case, the medium moves in a direction perpendicular to the direction that the waves move. If you look at this waveform that you see below, the waves are moving left to right. The medium itself moves up and down as the waves move left to right through the medium. So if you look at any one particular point in the medium as the waves move left to right, the medium will move up and then down as the wave moves through it. First above the rest position, then below the rest position. It'll go back and forth and back and forth. And that's the behavior of a transverse wave. So the key thing is that the medium moves in a direction perpendicular to the direction of travel of the waves. A couple things about this diagram that you want to look at closely. This symbol is a Greek lowercase l. It's a lambda. It indicates the wavelength. It's effectively the length of the wave from the location on one wave to the same location on the next wave. In this case, we're looking at the wave crest here, which we'll get to in a moment, to the next wave crest. This would represent one wavelength. We could also measure it from this rest position through one full wave to this rest position. So we could look at that as the wavelength. We could measure from a trough to a trough over here. All of these would indicate the wavelength of the wave. Usually has units of length for meters most of the time. Another way to measure the size of a wave is the amplitude. It's indicated with a capital A here on the diagram. You'll note that the amplitude is the same for each wave pulse. The wave crest and the trough are the same displacement from this rest position. The amplitude indicates the maximum deformation from the rest position. This rest position is where the medium would be if there were no waves moving through it. The more energy a wave has, the bigger its amplitude. This is one way that waves are different from objects. The energy in a wave, as we'll see, the energy in a wave has no dependence on how fast the wave is moving. So if you have two waves with different amounts of energy moving through the same medium, they will move at the same speed, but the wave with more energy will have a greater amplitude, and the medium itself will move a greater displacement away from the rest position. So v is the wave velocity, again the speed and direction of the waves through the medium. This is a property of the medium itself and not necessarily of the waves. So the medium itself will have a characteristic wave speed. Now when we look at this transverse waveform, we've got what's called a crest and a trough. Effectively, they are the maximum displacements or the amplitudes on either side of the rest position. Once we assign one side of the rest position as a crest, the other side is a trough. This is directly related to water waves. You can imagine a wave cresting. It's up higher than the water surface, and then the trough is the low point in between. Now, the other type of wave we're going to look at is a longitudinal wave. In this case, the medium moves in a direction parallel to the direction of wave motion. So we have, instead of a crest and a trough, we have what's called a compression and a rarefaction. The medium itself is compressed or sort of squashed together at the compression and then stretched apart at the rarefaction. Again, from one compression to the next, we would measure the wavelength. From one rarefaction to the next, we could also measure the wavelength here. The best example of longitudinal wave is a sound wave. Most of the time, air is the medium for sound waves, unless you happen to be underwater. But most of the time, you're in the air, and the air carries the longitudinal compression wave from the source of the sound to your ears. We'll get to sound and hearing a little later on. Now, some other wave quantities of interest. We need to know about the period. This is given the symbol capital T. We've used this before for circular motion. In the context of waves, the period is the time it takes for one full wave to pass a single point in the medium. So when we look at the transverse waveform, the medium goes from the rest position up to the wave crest, back down through the rest position to a wave trough, and then back up to the rest position. That's the time that takes would be the period of the wave. So usually units of seconds. The frequency of a wave is the reciprocal of the period. So if you think of the period as the seconds per wave, frequency is the reciprocal, and that's waves per second. The metric system unit for frequency is hertz, given the symbol capital H, lowercase z, Hz. Again, this is equivalent to a wave per second. Not too many people listen to the radio anymore, but FM radio is measured in MHz or megahertz, and AM radio is measured in kilohertz, KHz. The metric prefix mega means million, kilo means 1,000. So the radio signal that's measured in megahertz has a wave frequency in the millions of cycles per second. Now, a couple of wave formulas that matter. On your formula sheet, wavelength lambda equals wave velocity divided by frequency. This is called the wave formula, works for any wave in any medium. Also written as V equals F times lambda, but on your formula sheet looks like this. Also, not on your formula sheet, the fact that the period and the frequency are reciprocals. T equals 1 over F and F equals 1 over T. Again, frequency is in hertz or waves per second. Period T is in seconds per wave, or just seconds. Okay, that's our introduction. Next up, we'll take a look at some simple harmonic motion, pendulums and spring mass systems. These are mechanical systems that have wave-like behavior. Until then, enjoy, and I'll see you again soon.